Okay, we're going to have a little look at example 8 on the friction section of this chapter. And friction is a concept that hopefully most of you are familiar with, right? Anytime I move an object along, so if I apply a force to my mobile phone along a piece of paper, there will be a resistance force trying to stop me from moving or making it harder for me to push my mobile phone, and that's friction. Now, in terms of the mechanics of it, the mathematics of the situation, we have a relationship that's very clear for friction that can be calculated, and friction depends on two things. So when we're moving, and this is important, when we are moving, or I should say when we are accelerating, so that is when the forces are unbalanced and you're moving in a certain direction and friction is just a resistance, we have that friction force is equal to mu times r. So here we have that R is the reaction between the surface, that's the R force that we've been familiar with throughout. So that basically will take into account the weight of the object, so it's how much force acts on each other, because obviously a heavier object is going to make it harder to push along, so it's going to offer more of a force. And the other thing is this mu. Now mu is the coefficient of friction. And this basically takes into account how rough the two surfaces are. So obviously if you try and move along something along a sheet of ice, you're going to find that thing slips right across. As soon as you apply a little force, it'll just go flying off. So there's very little friction on ice. So the coefficient of friction in that case would be extremely low. On the other hand, if you're trying to push something across a really thick carpet, then there's going to be a high coefficient of friction between the object. You might also see if you're trying to stop a door from being difficult to open, you might lubricate the door. Again, that's all about reducing the coefficient of friction, so making it easier, so there's less of a resistance force for you to do something. So let's have a look at how this works in example 8. So example 8 describes a particle that's of mass 5 kilograms, and it's pulled along a rough horizontal surface. So this word rough tells you that there's friction. By a horizontal force of magnitude 20 newtons. So let's get a diagram going. So 5 kilograms, so 5g downwards. We're then being pulled by 20 newtons, and our friction, right, is resisting against the direction of motion. Obviously, friction is always stopping motion, right? So whichever way we're moving, whichever way we're accelerating, friction will be going in the opposite direction. Now, if we look, we can have the reaction force, obviously is here, and for us to get this frictional force, we need to use friction equals mu times r. So it also tells us mu in the question, mu is 0.2. So we're still going to do exactly the same things we were doing before. We're going to resolve upwards, we're going to resolve horizontally, we're going to use F equals ma. It's just with this added bonus that we're now using friction is mu r. So let's start by doing the vertical resolving. So obviously it's not moving up and down, so that tells us that this r has got to balance with the 5g. So r is 5g, which is going to be 49 newtons. On the other hand, when we go horizontally, right, we know that we're accelerating because it tells us being pulled along, so that the movement is taking place. And if we are accelerating, then what we must have is we must start with the forces. So we're accelerating in the direction of 20, and then the friction is opposing, so it'll be a negative force. And then we can put this into F equals ma, which is 20 minus friction equals 5a. And of course, a is what we want to find as well as a frictional force. So now, because I've got friction, I know that this is mu r, I can replace it in my equation. So 20 minus mu r equals 5a. And we can put those numbers in. So mu is 0.2 and r was 49. So 0.2 times 49 equals 5a. This is 20 minus 9.8 equals 5a. And actually that's going to be important as well. So that 9.8, that was the frictional force, right? Mu r is equal to 9.8 because that is actually part A of the question. So then we subtract them, we get 10.2 equals 5a, we divide it, and we get that a is going to be 2.04 meters per second squared. And that is the answer to part B. Okay, so we've got part A, I'll just write the answers at the side. Part A was that our friction, which was equal to mu r, 0.2 times 49, which I did here, is 9.8 newtons. And part B, our acceleration, is 2.04 meters per second squared. Okay, so all we've introduced in this example is that when an object is moving, the friction will be equal to mu times r, where r is the reaction force and mu is this mysterious coefficient of friction.